Good morning everyone. Myself Indranil Mondal, Assistant Professor in Mechanical Engineering Department. I will discuss combustion and combustion chambers related to internal combustion engines and automobile engineering. Let's start the session. These are the main contents: NOC limited parameters, effect of engine variables in NOC, combustion chamber design, and types of combustion chambers. Let's discuss one by one. NOC limited parameters: compression ratio, inlet pressure, and indicated mean effective pressure. NOC limited compression ratio. The NOC limited compression ratio is obtained by increasing the compression ratio on a variable compression ratio engine until incipient knocking is observed. Any change in operating conditions such as fuel air ratio or in the engine design that increases the NOC limited compression ratio is said to reduce the tendency towards knocking. NOC limited inlet pressure. The inlet pressure can be increased by opening the throttle or increasing supercharger delivery pressure until incipient knock is observed. An increase in NOC limited inlet pressure indicates a reduction in the knocking tendency. NOC limited indicated mean effective pressure. The indicated mean effective pressure measured at incipient knock is usually abbreviated as CLEMEP. This parameter and the corresponding fuel consumption are obviously of great practical interest. An useful measure of knocking tendency called the performance number has been developed from the concept of NOC limited indicated mean effective pressure. This number is defined as the ratio of NOC limited indicated mean effective pressure with the fuel in question to NOC limited mean effective pressure with isooctane when the inlet pressure is kept constant. This performance number is related to octane number, and one of the advantages of this is that it can be applied to fuels whose knocking characteristics are superior to that isooctane. That is, it extends the octane scale beyond 100. Further simplification on the use of performance number requirements is done by introducing the concept of relative performance number, that is equal to actual performance number by performance number corresponding to the indicated mean effective pressure of 100. These are all about NOC limited parameters: compression ratio, inlet pressure, and indicated mean effective pressure. Engine variables that affect NOC. There are three factors that mainly affect the engine variables on NOC: density factors, time factors, and compression factors. Under density factors, compression ratio, mass of inducted charge, inlet temperature of the mixture, temperature of the combustion chamber walls, retarding the spark timing, power output of the engine. Under time factors, turbulence, engine speed, flame travel distance, engine size, combustion chamber shape, location of spark plug, and under compression factors, fuel air ratio and octane value of the fuel. Let's discuss one by one. First, density factors. Any factor in the design or operation of an engine which tends to reduce the temperature of the unburned charge should reduce the possibility of knocking by reducing the temperature of the end charge for auto ignition. Similarly, any factor which reduces the density of the charge tends to reduce knocking by providing lower energy release. Compression ratio. Compression ratio of an engine is an important factor which determines both the pressure and temperature at the beginning of the combustion process. Increase in compression ratio increases the pressure and temperature of the gases at the end of the compression stroke. This decreases the ignition lag of the end gas and thereby increasing the tendency for knocking. The overall increase in the density of the charge due to higher compression ratio increases the pre-flame reactions in the end charge thereby increasing the knocking tendency of the engine. The increase in the knocking tendency of the engine with increasing compression ratio is the main reason for limiting the compression ratio to a lower value. Mass of inducted charge. A reduction in the mass of the inducted charge into the cylinder of an engine by throttling or by reducing the amount of supercharging reduces both temperature and density of the charge at the time of ignition. This decreases the tendency of knocking. Inlet temperature of the mixer. Increase in the inlet temperature of the mixer makes the compression temperature higher, thereby increasing the tendency of knocking. Further, volumetric efficiency will be lowered. Hence, a lower inlet temperature is always preferable to reduce knocking. It is important that the temperature should not be so low as to cause starting and vaporization problems in the engine. Temperature of the combustion chamber walls. Temperature of the combustion chamber walls play a predominant role in knocking. In order to prevent knocking, the hot spots in the combustion chamber should be avoided, since the spark plug and exhaust valve are two hottest parts in the combustion chamber. The end gas should not be compressed against them. Next, retarding the spark timing. By retarding the spark timing from the optimized timing, that is having the spark closer to top dead center, the peak pressures are reached further down on the power stroke and are thus of lower magnitude. This might reduce the knocking. However, the spark timing will be different from the MBT timing. This will affect the brake torque and power output of the engine. Next, power output of the engine. A decrease in the output of the engine decreases the temperature of the cylinder and the combustion chamber walls and also the pressure of the charge, thereby lowering mixer and end gas temperatures. This reduces the tendency to knock. Next, time factors. Turbulence. Turbulence depends on the design of the combustion chamber and on engine speed. Increasing turbulence increases the flame speed and reduces the time available for the end charge to attain auto ignition conditions, thereby decreasing the tendency to knock. Engine speed. An increase in engine speed increases the turbulence of the mixer considerably, resulting in increased flame speed and reduces the time available for pre-flame reactions. Hence, knocking tendency is reduced at higher speeds. Next, flame travel distance. The knocking tendency is reduced by shortening the time required for the flame front to traverse the combustion chamber. Engine size and spark plug position are the three important factors governing the flame travel distance. Engine size. The flame requires a longer time to travel across the combustion chamber of a larger engine. Therefore, a larger engine has a greater tendency for knocking than a smaller engine, since there is more time for the end gas to auto-ignite. Hence, an spark ignition engine is generally limited to size of about 150 mm bore. Combustion chamber shape. Generally, the more compact the combustion chamber is, the shorter is the flame travel and the combustion time, and hence better anti-knock characteristics. Therefore, the combustion chambers are made as spherical as possible to minimize the length of the flame travel for a given volume. If the turbulence in the combustion chamber is high, the combustion rate is high, and consequently combustion time and knocking tendency are reduced. Hence, the combustion chamber is shaped in such a way as to promote turbulence. Location of spark plug. In order to have a minimum flame travel, the spark plug is centrally located in the combustion chamber, resulting in minimum knocking tendency. The flame travel can also be reduced by using two or more spark plugs in case of large engines. These are the density factors and time factors. Next, compression factors. Before going to compression factors, let's see the slides. Density factors I have told earlier. This slide I also discuss. These are the time factors that I have already told. Next, composition factors. Once the basic design of the engine is finalized, the fuel air ratio and the properties of the fuel, particularly the octane rating, play a crucial role in controlling the knock. Fuel air ratio. The flame speeds are affected by fuel air ratio. Also, the flame temperature and reaction time are different for different fuel air ratios. Maximum flame temperature is obtained when equivalence ratio is equal to 1.1 to 1.2, whereas equivalence ratio equal to 1 gives minimum reaction time for auto ignition. This figure shows the variation of knock limited compression ratio with respect to equivalence ratio for isooctane. The maximum tendency to knock takes place for the fuel air ratio, which gives minimum reaction time. Thus, the most predominant factor is the reaction time of the mixer in this case. In general, except at reach end, the behavior in the engine follows the same pattern as the fuel air ratio versus reaction time. The drop in MEP at very reach end is caused by large drop in thermal efficiency. Octane value of the fuel. A higher self-ignition temperature of the fuel and a low pre-flame reactivity would reduce the tendency of knocking. In general, paraffin series of hydrocarbon have the maximum and aromatic series the minimum tendency to knock. The naphthalene series comes in between the two. Usually, compounds with more compact molecular structure are less prone to knock. In aliphatic hydrocarbons, unsaturated compounds show lesser knocking tendency than saturated hydrocarbons, the exception being ethylene, acetylene and propylene. These are all about composition factors, fuel air ratio and octane value of the fuel. Let's discuss combustion chamber for spark ignition engines. The design of the combustion chamber for an spark ignition engine has an important influence on the engine performance and its knocking tendencies. The design involves the shape of the combustion chamber, the location of spark plug and the location of inlet and exhaust valves. Because of this importance, the combustion chamber design has been a subject of considerable amount of research and development in the last 50 years. It has resulted in the raising of the compression ratio of the engine from 4 before the First World War period to 11 in the present times with special combustion chamber designs and suitable anti-knock fuels. The important requirements of an spark ignition engine combustion chamber are to provide high power output with minimum octane requirement, high thermal efficiency and smooth engine operation. Combustion chambers must be designed carefully, keeping in mind for some general objectives. Smooth engine operation. The aim of any engine design is to have a smooth operation and a good economy. This can be achieved by moderate rate of pressure rise. The rate of pressure rise can be regulated such that the greatest force is applied to the piston as closely after TDC on the power stroke as possible, with a gradual decrease in the force on the piston during the power stroke. The forces must be applied to the piston smoothly, thus limiting the rate of pressure rise as well as the position of the peak pressure with respect to top dead center. Reducing the possibility of knocking. Reduction in the possibility of knocking in an engine can be achieved by reducing the distance of the flame travel by centrally locating the spark plug and also by avoiding pockets of stagnant charge. Satisfactory cooling of the spark plug and of exhaust valve area, which are the source of hot spots in the majority of the combustion chambers. Reducing the temperature of the last portion of the charge through application of a high surface to volume ratio in that part where the last portion of the charge burns. Heat transfer to the combustion chamber walls can be increased by using high surface to volume ratio, thereby reducing the temperature. High power output and thermal efficiency. The main objective of the design and development of an engine is to obtain high power as well as high thermal efficiency. This can be achieved by considering the following factors. A high degree of turbulence is needed to achieve a high flame front velocity. Turbulence is induced by inlet flow configuration or squeeze. Squeeze can be induced in spark ignition engines by having a bowl in piston or with a dome-shaped cylinder head. Squeeze is the rapid radial movement of the gas trapped in between the piston and the cylinder head into the bowl or the dome. High volumetric efficiency, that is more charge during the suction stroke, results in an increased power output. This can be achieved by providing ample clearance around the valve heads, large diameter valves and straight passages with minimum pressure drop. Any design of the combustion chamber that improves its anti-knock characteristics permits the use of a higher compression ratio, resulting in increased output and efficiency. A compact combustion chamber reduces heat loss during combustion and increases the thermal efficiency. Different types of combustion chambers have been developed over a period of time. Some of them are shown in these PPTs. First type is T-head type. This was first introduced by Ford Motor Corporation in 1908. This design has following disadvantages. Requires two camshafts for actuating the inlet valve and exhaust valve by two cams mounted on the two camshafts. Very prone to detonation. There was violent detonation even at a compression ratio of 4. This is because the average octane number in 1908 was about 40 to 50. The T-head combustion chambers were used in the early stage of the engine development. Since the distance across the combustion chamber is very long, knocking tendency is high in this type of engines. This configuration provides two valves on either side of the cylinder, requiring two camshafts from the manufacturing point of view. Providing two camshafts in is a disadvantage. L-head type combustion chamber. This was first introduced by Ford Motor in 1910 to 1930 and was quite popular for some time. A modification of the T-head type of combustion chamber is the L-head type, which provides the two valves on the same side of the cylinder and the valves are operated by a single camshaft. This design has an advantage both from manufacturing and maintenance point of view. A modification of the T-head type of combustion chamber is the L-head type, which provides this type of configuration. The main objectives of the Ricardo's turbulent head design from this figure are to obtain fast flame speed and reduce knock. The main body of the combustion chamber is concentrated over the valves, leaving a slightly restricted passage communicated with the cylinder, therefore creating additional turbulence during the compression stroke. This design reduces the knocking tendency by shortening the effective flame travel length by bringing that portion of the head which lay over the further side of the piston into as close a contact as possible with the piston crown, forming a quench space. The thin layer of gas loses its heat rapidly because of large enclosing surface, therefore avoiding knocking. By placing the spark plug in the center of the effective combustion space slightly towards the hot exhaust valve, the flame travel length is reduced. What are the main advantages? Valve mechanism is simple and easy to lubricate. Detachable head easy to remove for cleaning and decarburizing without disturbing either the valve gear or main pipe work. Valves of larger sizes can be provided. What are the main disadvantages? Lack of turbulence, as the air had to take two right angles turns to enter the cylinder, and in doing so much initial velocity is lost. Extremely prone to detonation due to large flame length and slow combustion due to lack of turbulence. More surface to volume ratio and therefore more heat loss. Extremely sensitive to ignition timing due to slow combustion process. Valve size restricted. Thermal failure in cylinder block also. In I-head engine, the thermal failure is confined to cylinder head only. I-head type or overhead type. Main I-head type or overhead valve. The disappearance of the side valve or L-head design was inevitable at high compression ratio of 8:1 because of the lack of space in the combustion chamber to accommodate the valves. Diesel engines with high compression ratios invariably used overhead valve design. Since 1950 or so, mostly overhead valve combustion chambers are used. This type of combustion chamber has both the inlet valve and exhaust valve located in the cylinder head, and overhead engine is superior to side valve engine at high compression ratios. Some of the important characteristics of this type of valve arrangement: less surface to volume ratio and therefore less heat loss, less flame travel length and hence greater freedom from knock, higher volumetric efficiency from larger values or valve lifts, confinement of thermal failures to cylinder head by keeping the hot exhaust valve in the head instead of the cylinder block. This is all about I-head type or overhead type valve. What are the main advantages? Lower pumping losses and higher volumetric efficiency from better breathing of the engine from larger valves or valve lifts and more direct passageways. Less distance for the flame to travel and therefore greater freedom from knock, or in other words lower octane requirements. Less force on the head bolts and therefore less possibility of leakage. The projected area of a side valve combustion chamber is inevitably greater than that of an overhead valve chamber. Removal of hot exhaust valve from the block to the head, thus confining heat failures to the head. Absence of exhaust valve from block also results in more uniform cooling of cylinder and piston. Lower surface volume ratio and therefore less heat loss and less air pollution. Easier to cast and hence lower casting cost. These are the main advantages of I-head type combustion chamber. F-head type. In such a combustion chamber, one valve is in head and other in the block. This design is a compromise between L-head and I-head combustion chambers. One of the most F-head engines, that is OS type, is the one used by the Rover company for several years. Another successful design of this type of chamber is that used in Willys Jeeps. These are all about combustion chambers. What are the main advantages of F-head type combustion chamber? First, high volumetric efficiency, maximum compression ratio for fuel of given octane rating, high thermal efficiency. It can operate on air-fuel ratios without misfiring. What are the main disadvantages of F-head type combustion chamber? This design is the complex mechanism for operation of valves and expensive special shaped piston. These are all about combustion and combustion chambers. If you want to get more videos, please like, share and subscribe my channel. Thank you.